I'm Galen White.
And I'm Hannah Stepanek.
And our project is Light Up battery charging shoes. Today's consumers are bombarded with devices that harvest energy, but very few products combine the need for sustainability with the new market niche of integrating technology into clothing and other accessories. Our objective is to create a pair of Light Up battery charging shoes that harvest enough energy to charge 2 lithium-ion 3.7 volt 800 milliamp hour rechargeable batteries stored in the shoe's heels. 3 methods will be used to harvest energy. A piezoelectric sensor will convert the pressure from the user's steps into charge. A Peltier thermogenerator will harvest heat energy from the user's feet, and plates at the insoles of the shoe will harvest static electricity generated from walking. The piezoelectric sensor will also be used to signal LEDs to turn on briefly with each of the wearer's steps. A separate, non-rechargeable battery will be integrated into the system just to power the LEDs. The wearer will have the choice of powering the shoes with either this or the batteries that have just been charged by the shoes themselves. The device will be fully functional, lightweight shoes, since the electronics and circuitry will add no more than 1 pound of weight to each shoe.
The minimum power requirement for one Peltier chip will be 3.4 milliwatts per hour. Peltier devices generate energy from a difference in temperature. They consist of many p-type and n-type pairs that generate current. One of these pairs is shown here. When the top of the device becomes hotter than the bottom, electrons flow from the n-type material toward the heat, and holes flow from the p-type material toward the heat. This motion of electrons and holes creates current within the device. This particular Peltier chip has 540 of these n-type p-type pairs. The voltage generated by a Peltier device is equivalent to the number of pairs times the Seebeck coefficient of the material multiplied by the change in temperature. In this case, the Seebeck coefficient is 270 microvolts per degrees Kelvin. The temperature of the bottom of a person's foot inside a shoe is about 94 degrees Fahrenheit. This was calculated by actually measuring the temperature of the bottom of a person's foot inside a slipper. The highest average temperature in Corvallis, Oregon during the winter months is about 81 degrees Fahrenheit, and the coldest average temperature is about 34 degrees Fahrenheit. This yields a maximum and minimum voltage calculation. The minimum voltage is 1.1 volts and the maximum voltage is 4.9 volts. The resistance of this particular chip is 300 ohms, which leads to a maximum current of 16.3 milliamps and a minimum current of 3.67 milliamps. The maximum power that can be generated from one Peltier chip is 80 milliwatts. These calculations are only for one Peltier chip, which is 3.4 millimeters by 4.3 millimeters. This means that at least 300 of these chips could easily fit inside one shoe, which of course will increase the power output substantially. The static charge is captured from the wearer of the shoes via a copper plate installed in the insole. The circuit pictured here simulates an electrostatic discharge of 10 kilovolts, which is large enough to hear and see and may last over 30 milliseconds. The 1.5 kilo-ohm resistor simulates the resistance of the wearer's foot. The 50-ohm resistor and the 470 microfarad capacitor represent the storage device on the other end. In this case, the electrostatic discharge would produce a power output of 50 nanowatts, lasting anywhere from 2 nanoseconds to 77 milliseconds. A more typical electrostatic discharge may only last for a couple nanoseconds and result in an instantaneous power output of only 4.2 nanowatts.
Piezoelectricity, which means electricity resulting from pressure, is the charge that accumulates in certain materials in response to applied stress and mechanical vibrations. Piezoelectric sensors use this effect to measure pressure and force and convert it into electrical charge. The piezoelectric sensor in this project will harvest energy from the vibrations and pressure in the user's footsteps. At a vibration frequency of 40 hertz, there is going to be an average power output of 0.25 milliwatts with an output voltage of 13.2 volts and a current of 19.9 microamps. The sensor will not only contribute to charging the batteries, but also trigger the shoe's LED display on with each step. Once the pressure of a step has been applied, a timer IC will cause each of the 5 rows of LEDs to light consecutively upward, and each row will be on for only 0.1 seconds. The full shoe LED display cycle will take approximately 0.5 seconds to complete.
So here we have the rectifier circuit with our three power sources: static electricity plate, piezoelectric, and Peltier generator modeled voltage sources on SPICE. Each power source is fed into a full wave rectifier, which will charge three separate capacitors, and the output of each capacitor will be fed into the input of the next rectifier. At the end of the rectification and adding process, each capacitor adds to the next and will reach a static DC voltage, which will be fed into the charger circuit.
This is one of the shoes we will be modifying for our senior design project. The piezoelectric, as we said earlier, will be located in the heel of the shoe here. The Peltier chips will be located throughout the entire insole of the shoe, and the static electricity conductive capturing plate, which will be made of copper, will be located near the toe of the shoe here. The rechargeable batteries will be removable via the heel of the shoe and will be located in the heel of the shoe here. And the shoe, once we're actually done with the project, will probably stand about this far off the ground.
We chose our block diagram to be the way it is because we started out with three environmental inputs, which we are harvesting three different ways. Those ways are the static plate, the Peltier thermogenerator, and the piezoelectric sensor. These power supplies power the rectifier circuit, which is then moved out into the battery charger circuit, which will charge the battery, and from the rechargeable battery, the battery will regulate itself via the voltage out. The rechargeable battery will also be used in the LED control to show how much charge is currently on the battery. We're hoping to get some kind of IC or microcontroller in order to control those things. The LED control is going to be powered almost exclusively by the auxiliary battery, and the auxiliary battery out will also power the LED display. The controller will also be dependent on user input, which should have like an on-off switch and a mode of how we're going to display on the LEDs. The auxiliary battery will power the controller, and it will also power the LED display. And the controller will set up the LED display via control signal CTRL, and it will choose how the LEDs will display, whether it be the charge on the batteries, an on-off, or any other kind of design that we choose that could be dependent on the piezoelectric sensor. And we also, the only thing outputted into the environment will be the light out from the LED display.
By November 14th, all the preliminary circuits for this project will be completed. By November 28th, all the final circuits for this project will be completed. The final design is due on December 5th. During winter break, all the parts will be ordered. By January 30th, all the circuits will be breadboarded, except for the LED display. By February 6th, the piezo, Peltier, static, and rectifier circuits will all be breadboarded and functional together. And the final LED display circuit will be breadboarded and functional. By February 20th, the piezo, Peltier, static, rectifier, and charger circuits will all be breadboarded and functional together. The LED display and control circuits will also be breadboarded and functional together. By March 5th, all of the circuits will be breadboarded and functional together. By March 12th, all the circuits will be soldered and functional together. The final prototype is due on March 19th. During spring break, the PCBs will be ordered. By April 16th, the piezo, charger, and static circuits will be functional. By April 30th, all of the PCBs will be functional individually, with the exception of the LED display. By May 7th, the piezo, static, Peltier, and rectifier PCBs will be functional together, and the LED display will be functional by itself. By May 21st, the piezo, static, Peltier, rectifier, and charger PCBs will all be functional together, as well as the LED display and LED control PCBs. By May 28th, all of the PCBs will be functional together, and by June 4th, all the PCBs will be functional together and inside the shoe. The final project is due on June 11th.
This presentation covered how we plan to implement a battery charging device in a pair of shoes. The three methods we will be using to harvest energy, which consists of the static plate, a Peltier thermogenerator, and a piezoelectric sensor. We also went over a rectifier circuit, our static electricity harvesting circuit, and a block diagram. We discussed the LED display and the planned modifications to the shoes we plan on using. In today's greed and obsessed times, it only makes sense to put a sustainability device into something like shoes. Combining fashion and sustainability is something that will become more and more prevalent over time.